Let's go on YouTube. YouTube. YouTube is working. Yeah, it's working. All right, good. Making progress. How's it going, Sarah? Let's get on X here. All right. X should be live any second now. How's everybody doing today? Got like a weird shadow effect on my head. It's strange. Alright, I think we're live on X as well. Let's confirm. It's taking a second. Go. X always takes so long. It takes like 30 seconds to go from being live to actually being live. I guess they don't have the same quality of streaming as YouTube. Okay, I think X is live. All right. Let's go ahead and get started, guys. All right, we got a cozy little stream today for you guys. It's called Animals versus Robots. In this stream, we're going to be reviewing a paper that's actually not even like a archive paper. This is a paper from Science Robotics called Why Animals Can Outrun Robots. So in this paper, they basically compare animals and robots and all the different parts of each and kind of, I think, paint a good picture about where we are in terms of creating artificial embodiments, how close we are to animals, and we can also think about that being how close we are to humans. So we're going to be spending some time. How's it going, Thai Vu? So let's start off with the introduction here. This is work from University of Washington Robotics Laboratory, SRI, University of Colorado Boulder, Georgia Institute of Technology, and Simon Fraser University, so quite a lot of different institutions there. Animals are much better at running than robots. The difference in performance arises in the important dimensions of agility, range, and robustness. To understand the underlying causes for this performance gap, we compare natural and artificial technologies in the 5 subsystems critical for running, power, frame, actuation, sensing, and control. With a few exceptions, engineering technologies meet or exceed the performance of their biological counterparts. And this is kind of the narrative that we're going to see throughout this paper, is that even though animals are better than robots at locomotion tasks, all the subsystems that robots have are actually better than animals usually. So it's like, even though robot muscles are stronger, even though robot energy density is stronger, even though like many of these different subsystems are better in the artificial version, for some reason the biology has an advantage, right? So why is that? So they're going to identify 4 fundamental obstacles that roboticists must overcome. Towards this goal, we highlight promising research directions that have outsized potential to help future running robots achieve animal-level performance. How's it going, James? All right, so there's a lot of different types of robots. In this paper, they're mainly going to be focusing on legged locomotion, which usually refers to basically either bipeds, quadrupeds, or even this little roach bot over here. So they define a runner or a robot that performs like a locomotion as something that has intermittent contact between the limbs and the terrain to move. Robots are assembled from discrete components at the macro scale, whereas animals are formed from heterogeneous structures grown at the nanoscale, and use different physical phenomenon and material for power, sensing, actuation, and control. How does it go in 87G end? If you guys have any questions, feel free to interrupt. The stream is pretty sleepy, so happy to go off track and talk about unrelated things if you guys have any questions. So how do we quantify the performance gap between robotics and animals? Should we have a range to operate dependently over the distances required, agility to reach and traverse surfaces in its environment, and robustness to maintain range and agility despite changes to the runner and its environment? So the ability to generalize and work in a variety of different environments, right? A lot of locomotion that you see is usually on flat ground, very simple environments, but you want to be able to see locomotion on rugged environments, slippery like snow, ice, steps, sand. There's so many different types of environments, and robots have a kind of a hard time dealing with all of them, versus I'm pretty sure if you put a cat on anything, it would largely be able to walk around. Range can be directly quantified as the distance traveled, determined by the onboard energy supply as well as the efficiency of energy conversion. So the farthest walk by a legged robot on a single battery charge was Ranger, which did a 65-kilometer trek over the course of 31 hours. Ranger is this robot right here, this little blue one. So they have this nice little three-dimensional plot where they have agility, range, and robustness. So looking at range, the robot with the largest range is this Ranger robot, and I actually have a little picture of it pulled up. This is the Ranger robot, a little bit old school, so you can tell based on the kind of dress that this was probably the 2000s, maybe even the 90s. But this was a robot in Cornell that was a walking robot, but it used a bunch of kind of passive tricks in order to be extremely energy efficient. So even though they kind of list it as the furthest legged robot in terms of energy efficiency and doing 65 kilometers round and round and round this track, not that. I don't feel like this is necessarily really representative, because this is a really artificial kind of track, right? It's like you're going around this loop, and I don't know. That doesn't really count. I'd love to see kind of how long one of these Boston Dynamic dogs can traverse a very rocky terrain, right? It probably can't even do that for more than an hour. Robot batteries have about 50-fold less useful energy per unit mass compared with animal fat. Exceptional athletes can run hundreds of kilometers over multiple days in a single outing. So it does seem like animals have the energy efficiency there, but they compare to batteries, whereas I feel like if you really wanted to be energy efficient, you could use gasoline. Gasoline is much more energy dense, but I don't know, it has a bunch of other disadvantages, to be honest. Animals can outrun and outmaneuver running robots. This one I thought was not necessarily true. So they say agility-wise, animals are better, but there's some pretty agile little robots, and for that I have pulled up here Japanese mini sumo, I think it's called, but it's a type of robotic competition that they have in Japan where you have these tiny little robots, and they compete in a game of sumo, right? So they're basically trying to knock each other off this circle. But the cool thing about this is that they're so fast that it's like two gerbils fighting, if you blink, you miss it. And you can see here that the strategy that this one has is to go all the way around and then push the other one out before it can even realize what's going on. And there's all kinds of meta strategies that they have too. So for example, here's another strategy where the little robot just it moves out of the way and it lets this one just completely go out. So I think these are the most agile robots I've ever seen, and they move way faster than anything, right? I don't know, I've never seen a cockroach move this fast, or any Maybe a rabbit. I don't know. Like even a rabbit, I feel like this thing has more instantaneous acceleration and the ability to change directions very, very quickly. But that's just because it's using wheels, right? So it's not quite legged locomotion, but I don't know. I do feel like there are robots that are more agile than human or than their biological counterparts. Robot range and agility decrease precipitously when large payloads are added. Animals excel at maintaining performance despite changes that would be catastrophic for existing robots. 5 subsystems: the power system to store and deliver energy, a frame for support and leverage, actuators to modulate the mechanical energy, sensors to perceive self and environment, and a control system to transmit and transform sensor and actuator signals. So let's look at this figure here because I tried to identify all the things here. So we have the cheetah, the human, the cockroach. We have the ranger, which we saw before, this one here. And then what are these other ones? So I identified this one. This one is called Cassie, which is this robot. Cassie is actually the predecessor to Digit, so it's the same company here, Agility Robotics, that made it. So Agility Robotics, the company that makes Digit, also made the original Cassie walker. Drag to see Cassie walk. Look at that. You can see kind of the gait that it uses, those famous backward knees that it's known for that are supposedly more energy efficient. It doesn't do any kind of like toe heel stepping or anything fancy like that. It just puts its foot flat on the ground. All right. What's the other robot? So the other robot we can look at here is maybe this one here. So this one down here, this is called the Dash, which is a little insect robot. This one is 2009, UC Berkeley. You can see it here. It's based on a cockroach, which is, I guess, a little bit creepy, but that's what it looks like. It has this kind of like alternating 6-foot gait here. Here it is kind of climbing a little thing. You see all that kind of like passive actuation there where like there's a bunch of stuff that's just in tension so that whenever you move around, it kind of has a springiness to it. Pretty cool. And then we got this one here. This one is also very recognizable. This is the Animal. Kind of looks like an animal, you know, so they called it the Animal. This is made by ETH Zurich. I think they actually spun it off into its own company now called Anybotics. So these guys are basically competing with Boston Dynamics. They sell these little quadrupeds mainly for inspection purposes. You can see here, 2016. Here's some videos of it moving around. This website that I've found, by the way, very cool. So this is like a website that has literally all the robots, or a lot of them, right? Not all of them because there's way too many robots, but look at this. They have robot rankings. This is badass. Look at that. All the different robots ranked by whatever you want. You have all the different humanoids here. You have Atlas, the new Atlas. It tells you the year, the company. They aggregate all the information for you. But Salamander robot. But I don't know. I thought this was kind of cool. They have a creepiest robot category. Like, what? Come here. The creepiest robot based on 42,000 ratings is this one here called the Telenoid. Telenoid is a robotic communication device. You connect to the robot over the internet and it will transmit your voice and mimic your face and head emotions. It's like a mobile phone shaped like an alien. Dude, this thing is unbelievably creepy. Why did they give it little nubby arms? That makes it even more creepy. Dude, this thing is so weird. Oh my god. Like, I feel like they tried to go for kind of like a... This is definition of Uncanny Valley here. Weighs 5 kilograms, height of 80 centimeters, so a little bit over a meter. So creepy. Let's look at the second creepiest robot. Second creepiest robot, Casper. Casper and CB2. Let's look at these other creepy robots. Ooh, I don't know what's creepier, the nubs or the little hands. The hands are pretty creepy too. See, why did they give it this wig? Child-size humanoid robot. Therapy for autistic children. I feel like this is just going to scare the autistic children. It's not going to provide therapy for them. Oh my god, dude, this thing is so creepy. Looks like SCP stuff. What do you mean by SCP? Including the biomimetic robots. There's a bunch of biomimetic robots on here. There's the this salamander one. Where is it? Yeah, there's the little cat robots, Ibo. I wonder if they actually have the snake robots. Let's see. Snake robots are actually what I... Whoa. It's thunder outside. You might have heard that. Snake. Explorer, Guardian S. Huh, they don't actually have the snake robot that I worked on in college. But do they have any of the fish robots? They don't really have a lot of fish robots either. All right, so maybe this website is not that great. There's a bunch of different fish robots, but... So, back to this, though. I couldn't find this one. This silhouette was the hardest to identify, this one right here. I think it might be this one. It might be Spacebach, which is an ETH Zurich robot, basically like an early predecessor to the Animal. But I don't know. That's my best guess for what this one is. It could be one of the early Boston Dynamic ones as well. How's it going, Tomcat? Lullaby robots. Let's see. Search robots. Lullaby. Lullaby. No robots match. Couldn't find it. Here, let's go back to rankings. Newborn. Most rated, really creepy. Oh my, dude, this thing crawls. Robotic infant simulator that focuses on the development. It can teach itself to crawl, sit, and stand. Dude, what? Oh, this is kind of cool. You see that? It's not, these are like the muscle actuators. I've seen these before. They're kind of a little bit of a gimmick. You see these muscles here? They're the like fake muscles that basically they expand and contract. So you're trying to create a robot using the same type of like design as biology has, where you have basically alternating things that contract, right? And then you have your quadriceps, your hamstring, your bicep, your tricep. They kind of alternate. But I don't know. I think those are kind of a gimmick. I think the electric motors are much more. That's probably what I would have to. What I guess would end up being the go-to. You know, that's what we see in the Atlas robot as well. Starship, Vector. There's some old timers here. The Furby. I don't know if the Furby's creepy. Darwin, Temmie. Cog, the Da Vinci robot. People think the Da Vinci is creepy. This is the surgical robot. So you see here the Da Vinci robot. People basically, you can do this from quite remote. It's been around for quite some time, 1999. But you basically control it in VR with these little kind of like pincers. That thing looks pretty creepy. I guess it is kind of creepy in a sense. That this is a famous video of someone making mini origami with this tiny little robot, but it's all teleoperated, right? That's not autonomous. That's what the controls look like. What is the goal of creating an infant simulator? Probably just to creep someone out, you know? Just to scare someone. I don't know. It's probably like most robotics is research, right? So Osaka University, 2009. Yeah, it's just kind of a research project, right? This robot isn't going to be used in production environments. You can just tell just based on all the exposed wires and all the stuff like that. This is not something that was designed for mass manufacturing. This is just a one-off kind of robot that they built in a lab just to publish a bunch of papers and then eventually that's it. You know, once the guy who built this is done with their PhD and they leave Osaka University, this robot's probably shelved. Here's more pneumatic actuation. 2006. Pretty old school, but it kind of works well. I don't know. Pneumatic muscles are light and simple and can run on compressed air. Yeah, compressed air is not... It has the same problem as hydraulics, though, is that then you have to have all this pneumatics crap associated with it, right? The company I was looking for is Festo. Oh, yeah, I've heard of this one before. They have the jellyfish robot and the flying robots. I've seen these guys before. Yeah. This one. They also have the kangaroo, the bat. They're pretty cool. I don't actually know, like, how they make money. Like, they always have these really cool robot concepts, but, like, what do they actually do for money? Like, does anybody buy, like, these dragonfly and kangaroo robots? I don't know. I think they have a gripper, too. There's a Festo gripper. Yeah, this one. So it's like a suction gripper. Maybe this one? I'm trying to find the video, but I'm trying to find it as a GIF so I don't get blocked by YouTube here. But it kind of like suctions up different items. Maybe 3 claw. Oh, this one is cool too. That's an octopus gripper. See, that's got little suction cups on it. But these are all prototypes, right? I think that the product that they actually sell is this thing here. It's like a parallel jaw gripper, right? So in this case, you just put whatever you want on there, and then it's two things. Festo is a private company. Yeah. But it's hard to like imagine they make enough money from their little parallel jaw grippers that they can basically have an entire internal division that just makes these like kind of gimmicky robots for demos. Yeah, like this seems to be their actual product line. It's just a bunch of grippers. All right, let's keep going into the power system. Power subsystem. Engines convert gas to movement, batteries convert chemical bonds to electricity, and metabolism converts fat to adenosine triphosphate. Oxidative metabolism within mitochondria converts fat to ADP with remarkable efficiency at about 70% compared to 25% in engines. Adipose tissue is almost 90% fuel. Gas tanks can be 20% of the mass of the fuel they carry. So batteries are worse than gas, right? But gas is still way off from fat and oxidative metabolism using mitochondria. And even in their appendix section here, so this is the appendix section where they have all the tables here, they had one really cool chart here. Yeah, so this is the body mass of different animals, right? So cat is 5 kilograms, human 100 kilograms, okay. And then they make some back of the envelope math here where a single mitochondria, which is the part of the powerhouse of the cell, right? A single cell has about 300 mitochondria. And then using that, you can effectively come up with the body mass of mitochondria. Like what percent of your body mass is composed of mitochondria? And for a human, it's 0.19, which is tiny, right? 0.01% of your body mass is mitochondria, and all of your power production is coming from that 0.01% of your mass. And compare that to something like a battery, like a lithium-ion battery, or even a gas engine, right? The relative weight of your engine and your fuel tank, or of your battery and your like that is huge, and the efficiency is so much worse compared to mitochondria, which are these little like single-celled organisms that got absorbed into cells, which is kind of crazy to think about. We would probably not be here. Nothing would exist if mitochondria didn't exist. Everyone is depending on mitochondria for everything. But one thing that they do say here is that gas tanks can be refueled an order of magnitude faster than a battery can charge or digestion can process biological matter. So this is kind of a good point here, right? Where you can fill up a gas tank in minutes and then you can just immediately start going again, versus if you eat a bunch of food, it's going to take you a while to digest that and then be able to produce ATP and then power from that. So there is an advantage in kind of the ability to refuel very, very quickly if you're using gas, although batteries also have the issue of taking forever to charge. There are like swappable batteries. That's one thing I've seen before. Swappable batteries, moped. I think these are popular in kind of dense cities like this, right? Where basically you swap out batteries so you don't have to charge the battery. And then it also solves the kind of issue that you have with batteries slowly getting worse over time, so that you can keep the most of the robot, or in this case a moped, is not going to degrade as fast as the battery. So if you can swap out the battery, the lifetime of the entire moped or robot can be much longer. So I can imagine a situation like this, right, where if you have a bunch of little robots in your factory, right, they don't actually charge themselves. The battery is not directly built into the robot. It's more in this kind of like swappable kind of design. So I don't know, that would get rid of the negatives of having to charge your battery. We'll have to grow robots and have metazoan ones. Yeah, Saskia, that's also like, so, I mean, this is like way out here, but like, you know how one of the theories around the alien Greys, these guys, Greys, aliens, is that they're not like beings. What they are is robots. So Greys are basically robots that are being printed by some other species of alien that we don't know, right? And it actually kind of makes sense, right? After reading this paper, you realize that all the biology versions of these subsystems are so good that the reason our robots are mechanical is because our digital and kind of like metalworking technology and battery technology is way more advanced than our biological technology, right? But 100 years from now, if our biological technology gets really, really good and we can basically print out organs and we can print out cells and we can program the cell by just changing the DNA, right? Some kind of like next level version of CRISPR, then will we continue to make robots out of metal and with batteries that use electricity, that all the stuff is digital? I'm not entirely sure, right? I feel like maybe we're underestimating just how good biological technology is going to get. And then if biological technology gets really, really good, maybe we don't create metal robots. Maybe we create biological robots. And that's what these gray aliens are. They're basically just biological robots, right? That could be kind of cool. What if water is removed from the equation? Yeah, I guess that's a good point, right? The one benefit of electromechanical robots is that they're very resistant, right? You can deploy them in much more brutal environments, in environments that have no atmosphere, versus if you had some kind of biological robotic system, it would be much more sensitive, but also it'd be biodegradable, So like you could have a bunch of robots that are like little aliens, little gray aliens, and then if they break down, whatever, they just fall down dead and then just rot, and then that's it. They're 100% biodegradable, versus like a metal robot like that. It wouldn't break down. So they're more eco-friendly. Unfolding one where at the end an algae will be able to fix by itself nitrogen. Yeah, maybe some kind of biodegradable plastic. Okay. Talking about biodegradable plastic, the next subsystem that they explore, so they were looking at the power subsystem, is the frame subsystem. Actually, why don't we review here? So in the power. So this is a nice little chart here. So for power, specific stored energy, which is kilowatt hours per kilogram, specific delivered power, which is kilowatts per kilogram, and then specific refueling power, kilowatt per kilogram. So engine, battery. So an engine can refuel very quickly, so 10 to the fourth, which is way bigger than metabolism at 1, or a battery at 0.2. So a battery is worse than the biological component, but a gas engine is better. In terms of power, right, electric motors have all their torque instantaneously available versus usually engines you have to slowly build up the RPMs in order to actually get to a higher amount of power. So electric is beating both the engine and the biological component in terms of delivered power. But then in terms of the stored energy, right, fat metabolism and mitochondria consuming that and turning it into power, that's way more efficient than anything we have now, including the engine and the battery. So power seems kind of up for debate. Let's look at the frame. Running robot frames are generally built from rigid connections between steel, aluminum, or carbon fiber struts using linear or rotary joints. Vertebrates have an endoskeleton made from bone connected by soft tissue, and insects have an exoskeleton made from hard cuticle connected by soft flexures. Two different designs there. We generally tend to do robots in the vertebrate design, where you have basically like limbs and then stuff that actuates the limbs, rather than the insect design, where you basically have all the weight-bearing structure is kind of on the outside. But you know, the Cybertruck is actually kind of a little bit more insect-like, right? So in the Cybertruck, a lot of the load and weight bearing is being done by the actual exterior of the car rather than necessarily the chassis, right? Most cars, the exterior is kind of just there, and then the chassis is what's holding everything together. But I think in this car, they actually switched it around, so it's almost a little bit more like an insect in that way. We compare density-specific stiffness, defined as a material's modulus of elasticity normalized by its density. So basically, how much can material deform. Resilin is used in insect jumpers and in tendons in vertebrates. All right, let's look at this. Frame. Specific stiffness. Bone or cubicle less than 10 versus carbon fiber 100. So carbon fiber, which is probably the best material we have in terms of specific stiffness, but also like the reason that they're choosing carbon fiber here is because they're doing it by kilogram, right? So you see here how they, these are per kilogram. So anytime you're going to normalize by the mass, then carbon fiber is going to be the best, but it really is significantly better than bone or cuticle here. Not less than 90 to 500, so 10x, 10x, 3x. It's pretty powerful. Engineered frames built from carbon fiber can be much stiffer and stronger than biological skeleton built from bone. So I don't know, maybe we build a biological robot, but the biological robot is grown on carbon fiber bones, right? So like almost like the Westworld 3D print, right? This is an old show, but in this show, they basically seemingly dip like some kind of like skeleton into like this bath, and then they 3D print it. So maybe that's the type of robot we see, right? Assuming the biology technology gets way better, we basically have carbon fiber bones, and we like dip that into this like biological goop, and then we create basically synthetic muscles. I wonder if it would still have a digital brain or not. But yeah, it seems like you want maybe biological metabolism, artificial frame. And now let's look at the next one, actuation subsystem. Zytel plastic would be perfect for bones. Let's see this. Zytel plastic. Zytel is a thermoplastic polyamide and the trademark of Celanese for a variety of nylon plastics that are strong, stiff, lightweight, and resistant to abrasion and impact. Okay, so this is what they use for skis. Here's a bunch of different pieces. Yeah, I mean, plastics can be good. And when you think about it, plastics are made from oil, which is made from dead biological material. So a lot of the strength and the compliance of plastics come from the fact that they're basically carbon chains. So I almost think plastics are more biological than they are artificial, right? It's like they almost count more as coming from the biology side rather than coming from this electromechanical side, just because they originate from dead dinosaurs. You know, that's kind of one way of thinking about it. All right. Muscles can outperform direct drive motors and bimorph piezos by a factor of 2 to 5 in this metric. Specific torque versus specific power. Motors and piezos have an advantage over muscles in their efficiency of energy transduction, which can exceed 90%, whereas muscle fiber efficiency in most animals is closer to 30%. Hydraulic actuators may exceed the torque and power density of motors, but their efficiencies are often much lower than either, and they require a complex and heavy fluid system. Yeah, this complex and heavy fluid system, I think, is the reason why they really stopped using that. So like the latest version of Atlas basically threw away their hydraulic actuation, and now they're going all in on the electric, because not because the electric is better in terms of these power density and torque. It's just because you don't have to deal with this heavy fluid system. And also the fluids that you use in these hydraulic systems are like kind of toxic, I'm pretty sure. So like you wouldn't want a robot that's in your house that literally has like toxic blood just all over it, right? I think the relative toxicity of an electric motor is a lot lower than these kind of hydraulic systems. It's less dangerous too, because if you were to like pop one of those hydraulic systems, it would like spray out. You know, imagine like a little kid accidentally like getting popped with one of these hydraulic fluid systems. Sensing subsystem. All right. Sensing subsystem. The number of rod and cone cells in a human eye is comparable to the number of pixels in the latest smartphone. So we're already kind of getting past that. Humans have roughly 200,000 tactile receptors in addition to 50,000 stretch receptors. That we definitely don't have. So in animals, neural activity in sensory regions can be substantial. 8% of resting metabolic rate for the blowfly retina. During movement, metabolism may increase up to 50-fold. So this is here in the diagram, they show this based on these little stretch receptors here, right? And even each of your little hairs has little receptors on it too, right? So that's something where we are completely outgunned, right? Like look at this, number of sensors, 10 to the 4th compared to less than 100. Right? Like in a robot, you might have an IMU, or an accelerometer basically, that tells you the orientation. But even in a robot like this, like there's probably only a handful of IMUs, if there's even more than one. Right? Compare that to a biological system where you have tens of thousands of these tactile receptors and 50,000 stretch receptors. And not only are those receptors much more numerous in a biological system, but they're also more directly tied into the control mechanism, right? So biological systems have this whole kind of repertoire of instinctual behaviors that don't need to go all the way to your brain, right? So whenever you put your hand on something hot and you pull it back, the reason you can pull it back so fast is because that signal doesn't even need to go all the way to your brain. It basically it almost has a more direct way to send a control signal to your muscle cells that are close, right? So this kind of distributed control strategy that pretty much all biological systems have is pretty OP. We don't really have anything in the electromechanical world that's even close yet. But when it comes to the actual observation space, so here photoreceptors, we're pretty much there. We have just as many pixels as the human eye. Electric noise, though. What is a motor? With a motor in every joint, it would be quite the orchestra. Okay. Let's look at this. Control subsystem performance. Bandwidth and latency fundamentally limit controller performance. Bandwidth of a standard Ethernet cable is at least 10,000 times greater than the fastest single axon, but a bundle of 1 million human axons has comparable area and period-specific bandwidth. Period-specific latency is at least 1,000 times longer in nerves than in an Ethernet cable. Period-specific latency is in the order of milliseconds for natural neurons and shorter than microseconds for artificial neurons. So this is definitely true, right? Is that the speed of communication in electric digital systems is way faster and the latency is way faster compared to biological systems, right? But part of that is that also the messages that you're sending are also way more heavy, right? So whenever you're sending information through an Ethernet cable, that information is being compressed into some digital signal that's getting sent, right? Some kind of TCP, UDP type protocol. That is probably an order of magnitude less information dense than the signal that gets sent via your neurons, right? Your brain, even though they send things much slower, the information that is being sent, I think, is compressed so much better, right? Your brain or any kind of system of neurons, they're fundamentally taking some input that is high dimensional and compressing it down via a hierarchy of neurons into a very compressed kind of low dimensional representation of the original signal. So even if that compressed low dimensional representation of the original signal is being passed very slowly from neuron to neuron to neuron compared to the information through an Ethernet cable, the total amount of information going through is probably more than the total amount of information that we can send through Ethernet cables right now. Or maybe not, I don't know, Take a look at the new Tai Chi processor. Yeah, I think that right now when we send information over Ethernet, we're sending information that is basically encoded text, right? But once software kind of 3.0, which is the AI, right? If everything is a neural net, then maybe what you're sending back and forth through the Ethernet is just vectors and embeddings. And once you're just sending embeddings and vectors back and forth, then the information density and the latency that you can get through Ethernet will be way faster than what you can get biologically. But until then, we don't know. Animals cannot practically decrease sensory motor delay by the orders of magnitude that would be required to compete with a robot communication channel. Favoring the use of internal models. Let's go back to this. So a myelinated nerve has a specific latency of 10 to the negative 3 versus a network cable 10 to the negative 6, and a bandwidth of 10 to the 13th compared to the 10 to the 16th. So multiple orders of magnitude, 3 orders of magnitude improvement in the digital versus the biological there. But in a brain, number of neurons 10 to the 11th versus 10 to the 6th. Number of synapses 10 to the 15th versus 10 to the 8th. So even though we got the advantage here in the digital realm of latency and bandwidth, we're still behind in terms of the total number of neurons. Also the energy efficiency of this, right? We have language models and vision language models that have a huge amount of parameters comparable to the number of neurons in your brain, but the energy efficiency of your brain and the neurons in there is still way better. They don't really have a number for that, but I just need a robot to make me sushi. I don't care how fast. Yeah, I mean, imagine like a little home robot that's in your house and it just does everything at night, right? So like the robot doesn't need to be fast, right? The robot can just be very, very slow and only work at night, right? So like when you go to sleep, that's like a good 7-hour chunk of time where your house is basically empty and nothing is happening. So you could have a robot that wakes up when you go to sleep and then it goes to your kitchen and it takes it 4 hours to make a plate of sushi, but because it's very, very slowly grabbing and very, very slowly placing and very slowly doing this. But if you wake up and you already have your food prepared by your robot and it did your dishes and it cleaned your house and then it's just sitting in its little charging station, that's still really useful, right? This is a medical robot, Moxie. This one goes around in a hospital. It can take the elevator, grabs things for you. Look at that, it's waiting. It has a little robotic gripper, little parallel jaw gripper. You see that Intel RealSense on the front there. How many DOFs in this arm? 1, 2, 3, 4, 5, 6, 7 DOF arm. You know, you want a lot of degrees of freedom so that you can get the end effector in whatever pose possible. The wheels are also useful because in a hospital environment, you're always going to have to be compliant to like wheelchair situations. So that's actually kind of a genius move, is doing things in a hospital. Look at that. They have another Intel RealSense down here. Little laser scanner. Another laser scanner. Lots of sensing here. I don't think you need these. I think eventually you're going to do everything with an RGB camera, multiple RGB cameras. I don't think you need these time of flight, LiDARs, structured light, kind of explicit 3D sensors I'm generally against. Chinese S1 robot is already not so slow. Let's see. Chinese S1 robot. Oh, yeah, I saw this one, dude. The Astrobot. So good. If you guys haven't seen this one, it's pretty next level. Let's see if we can find... I feel like this stream is going to get sniped anyways. You know, they're going to demonetize it just because I'm going to show YouTube videos. Might as well just show YouTube videos, but... Yeah, they released this, and this is cup stacking. So this is... It can stack cups at 1x speed faster than a human. Well, not really, because humans are very good at this, but look at the speed of that. This is slowed down, so this is 1/4 speed. So good, right? This is 1x. But I think this is teleopt. Or no, this is end-to-end autonomy. Okay. This is Corey with the figure robot. Damn, this is a nice little summary of all the robots. I also feel like people are sleeping on China as a robots powerhouse because all the components are made in China anyways. You know, like all the electric motors, all the cables, all the shit is made in China. So a robotics company in China that can fully vertically integrate is going to have a way easier time. And also they have a bunch of other advantages too, right? In China, the government is going to basically heavily subsidize your company, and you also have a large pool of talent that is cheaper, right? So I actually think the software problem in robotics is easier than the hardware problem. It used to be that the hardware was easier than the software, right? There was the PR2 demo. Whenever this first came out in 2010, like they teleop this. So hardware has been, I don't want to say solved, but it's been possible for decades now. You have even older than this, you had the Asimo robot, right? This was like the 2000s. They already had a walking humanoid in terms of hardware. And it really was the software that was difficult. Right, here's the 2000 Asimo. But the software now is really easy, right? Because I actually think that you're going to see like end-to-end a VLM, right? Some kind of generic open source vision language model that you just fine-tune on some robot data, and that might even work, right? I know that that's a little bit difficult to think about, but the RTX papers kind of point to that, where you're just going to have a simple end-to-end foundation VLM, and they're just going to be so good that you won't need to have all this specific stuff. So then, in that case, robotics is going to become a problem mostly around kind of packaging everything together such that it's like a clean system, right? So in that case, if you're operating in China and you can directly manufacture all this stuff, and you know, it feels like that's really what's going to matter. So I don't know. I don't think you can even buy stock for these companies because they're Chinese companies, but I feel like these guys are going to beat out the American companies just because there's going to be so much more capital efficient. I don't know. China has an aging population like Japan. Yeah, that's a big part of it too, right? Is that in the US, like, good luck trying to get the government to subsidize your robotics in the US, right? The US government is just such a mess. Versus in China, if you're doing some kind of robotic humanoid company, like, the government's going to give you money. So even if you can't raise money from some venture capital situation, the government will just give you the money because they're very interested in AI and robotics. All right. Let's see. Discussion. Although biological sensors are no more sensitive than their engineered counterparts, a large number of them can be distributed throughout the body, lending robustness through redundancy and benefiting agility by providing rich sensor streams for each body part. Yeah, this is kind of what we were talking about. There's just an order of magnitude more sensors in your muscles and your touch sensors, like the touch sensors on your skin. That's something that we're not even close to, right? There's the robot touch sensor. There's one that I think of. Yeah, like, look at these. These are terrible. These little tiny cheap ones, and the more expensive touch sensor finger. Where is it? Yeah, even look at this. Like, the amount. This is terrible. Look at that. What is that? Like 3x4, like you're talking about like a dozen touch sensors. You know, that's not even close. This is the one I'm thinking of. Yeah, these green ones. So if you've ever seen these green little fingertips, those are an interesting new type of touch sensor where it's basically looking at the deformation of this like little plastic piece, and then it gives you a much more information dense signal than these type of sensors here, which are basically just resistivity sensors. But these are very expensive. Like you're talking about even like $1,000 per finger. So we're still behind when it comes to touch sensing on hands. There's some cool stuff. Yeah, here's maybe a little breakdown. Fingerprinted skin, multimodal tactor sensor, strain gauge. There's also this one, gel site. You guys have ever seen this gel site robot sensor? Yeah, here we go. So this is pretty cool. This is like a completely different way of doing touch sensing, where they actually have a camera, right? So they use a little camera, and then that camera has like this gel on top of it, and then you can just look at the deformation of the gel and then treat that camera as if it was, rather than an array of pixel values, it's an array of pixel values that represent the touch interaction, right? And I think this is really cool because it's basically you're saying, okay, all these mechanical, like electrical resistance based touch sensors and kind of fancy touch sensors based, like those are all just never going to get to the resolution of your finger, but we have really good cameras, right? Like as they said here, like in terms of camera pixel density, like we're pretty much already there to your eye. So what if we turn the tactile problem into a camera problem? It's like an optical problem now. So you can do, you can collect a data set of this and then run all of your favorite like vision-based AI on this, right? You can do classification of the grasp, segmentation, like all the different things you can do with a pre-trained vision model. You can apply them to this type of task and turn the tactile sensing into basically just a vision task. Yeah, grasp success, and then you're just literally feeding these images into CNNs. See, this is kind of older research, right? Obviously now you would use something a little bit more advanced, but you know, transformer-based vision transformer as opposed to a ConvNet. But I thought that this research was really cool. I wonder if people are still doing this. In insects, each member has its own control plexus. Yeah, so you're basically saying that insects are even more so kind of along the line of that. This comment here where basically the control is distributed rather than centralized. Which we could probably do for robots too, right? You could imagine having little microchips at the legs and microchips in the hands that basically do some of the control without having to go all the way to the actual like central brain. And then you can even imagine like a next level version of that where the little chips that are providing this quicker control, like kind of feedback loop, are actually running little neural nets themselves. But I haven't really seen that before, even though that's a kind of a cool idea. When subsystems combine because of performance of one component might constrain that of the other, right? Your standard kind of engineering problem where you break things down into modules to kind of solve each of them individually, but then when you break them down into each of these different modules, whichever module is the hardest and one to create and has the worst performance kind of brings everything down. It is challenging to find good mechanical designs in the high-dimensional space of candidate designs and good control policies in the high-dimensional space of candidate policies. Yeah, actually, the space of candidate designs is huge, right? Like, think about all the different morphologies that we can have. And actually, what we pretty much do is we just use biology, right? When you look at all these robots, these all have like almost direct biological analogs. You see humanoids, you see snakes, you see quadrupeds, right? Like, these are all just bio-inspired. So you're using biology as a kind of way to filter through this high-dimensional space of designs. But there are designs that have no biological analog that are actually extremely powerful, right? Like, for example, the drones. There's nothing in biology that looks like a drone. You know, the spinning things, but drones are probably better than any bird, right? I feel like in terms of the raw speed and agility, like, is there any bird that is comparable with a drone? So there's probably maybe similar things in terms of like legged locomotion. There's probably like a weird type of like three-legged robot that is better than any type of four-legged or two-legged design. It's just that we haven't found it because we're just constraining ourselves to these biological designs. Good control policies in the high-dimensional space of candidate policies. I think we don't have to necessarily deal with that because this is going to be solved by AI, right? Like, you use the process of gradient descent and the fact that these deep neural networks are good function approximators to find the best control policy in the space of all possible control policies. So I think this will get solved, but I feel like this is still definitely an open question about like what is the optimal design for a robot. Some people are convinced it's humanoid, some people are convinced it's quadrupeds, some people are convinced that it's kind of more like the Moxie bot that we were looking at, where it's like kind of like a wheeled base with an arm on it. But even then, one arm, two arms, four arms, like, how many arms should this have? There have been 1,000 to 10 million times as many generations of animals as robots. Animals have been getting optimized via evolution for way, way longer than robots, so it kind of makes sense that they're way more performant in certain dimensions. But animals in one phylogenetic branch generally cannot benefit from innovations in any of the other ones. An adaptation that improves running in a cockroach provides no benefit to a cheetah. In contrast, advances demonstrated in one robot are readily transferred to the others. So, because you can take anything you learned with one robot and apply it to another robot, the progress in robotics is going to be way, way faster than the progress in animals, which took millions and millions of years. Hummingbird, dragonfly. I think those are good ideas. Hummingbird. Hummingbirds, pretty cool little animals. I think dragonflies actually might be more similar because dragonflies have four wings, which gives them the same way that drones, right? A drone has four rotors, which means that it can basically, it has enough degrees of freedom to control its space, its kind of position like this in space very easily, right? And dragonflies have the same trick where they have four wings, whereas most insects have two wings, right? So whenever you have two wings, you're going to have a harder time kind of like controlling where you are in space. But a dragonfly has four wings, so it has much better control over its movement, and that's why dragonflies have been around for so long. They're basically the crocodile of insects, right? In that they've remained largely unchanged for millions and millions of years because they're very, very good hunters, right? Dragonflies hunt other flying insects, and other flying insects only have two wings, so they can't compete with the four-winged dragonflies that are just faster and much more capable in terms of like doing fancy control in the air. An octopus robot to wash the windows. Are we dealing with the Dune movie? So people are talking here about the Dune ornithopter. This one here. How many wings does this have? 8. But I mean, this is not like a real system, right? This is like a made up thing. And doesn't actually make any sense. You know, we don't actually know if this is even possible. This was designed by a artist, not an engineer. Maybe they had an engineer come in and like consult a little bit, but I bet you, I don't know. I've yet to see a real life ornithopter that actually works. All right, let's keep going here. Bodies can be made easier to control by offloading computation and morphology. That's kind of the theme that we keep running into. What do we have here? Oh, this is another little interesting paper that I found kind of doing research for this paper. This is a paper released this week. Lessons learned in quadruped deployment in livestock farming. So this is like a paper where they deploy these little robots to herd sheep. So they're basically trying to herd, robotic herding. And they talk about the problems that they ran into. So limited endurance, right? Which makes sense. That's very in line with kind of what we were reading up here, where basically lithium ion batteries are just not good enough yet to basically last all day, which is a huge problem with these type of robots, is that they just, you can see this one, they tried to solve it. Like, I bet you a huge chunk of this like volume is just the battery. And maybe they figure out kind of some kind of swappable battery type situation. But right now, if you're trying to actually deploy these in the real world to do some sheep herding, basically the most annoying part is the fact that they can't run around all day, right? Like, versus like a sheep herding dog, like probably just feed it in the morning and then it works the entire day, versus these quadrupeds can't really do that. Quadrupeds need careful training, flock disturbance, so kind of the sheep are a little bit creeped out by the quadrupeds. I thought this was weird. The privacy and security of sensitive data related to the individual sheep. Like, what? People care about the data privacy of sheep? That's fucking weird. I didn't even think people thought about that. Protection of electronic components, right? So I think in any kind of like real world environment, especially kind of an agriculture environment like this, right? You need to be resistant to mud and dust and rain and just rocks and sheep poo, you know, and I don't really see that happening yet, right? Like, all you got to do is just look at here. You see all these exposed screws, right? You see all these exposed cables. If this thing like went into the water, it's dead. If this thing tried to like work in a dusty environment, the cameras would just get instantly covered in dust and then you're screwed, right? So like, we have that, and in biology, right, you have like you blink and you cry. So like, even though the vision sensor density is about the same in robots and animals have the ability to blink, and then they have the ability to cry to then get the dust out of their eyes. But like, we don't really have a good way to clear the cameras of these robots, right? Which is what they complained about here, is that when you're using these robots to herd sheep, eventually they just get covered in dust and dirt and poo, and you have to clean them, right? And you don't have to do that with a dog. Then they also ran into some initial investment burden, resistance to change, cultural resistant. Traditional farming communities may be resistant to change. I don't think that's as much of a problem. You know, I think that if you just wait 5 years, like, you know, these things are going to get good. People will get more comfortable with robots. And I think that the need to have kind of automation in these farms, right? Because every year, like, more and more farmers die and less farmers are born. So like the percentage of the human population that actually knows how to like run agricultural operations is like shrinking very, very quickly. I think this is a big problem in Japan too. Like, in Japan, the average age of like a farmer is like 65 or something crazy like that. So yeah, we might not be able to get the farmers right now to use robots, but I bet you the few farmers that we get in our generation will be more than happy to have a herd of robotic dogs that herd their sheep. It's just we need to fix the battery issues, and we need to fix the kind of resistance and like equipment protection. Will I be able to sit on my ass and enjoy post-scarcity with these robots, or will they find a way to mess this up? 87 GN. I don't think you do. I think, it's... So a lot of people will tell you, like, hey, you need to find a way to provide impact to the world. Like, you need to contribute. Like, you need to do your part. But I actually think it doesn't matter anymore. I think that we're very, very close to kind of, like, digital, like... AGI. Not that we're already at AGI, but we're very, very close to digital ASI. And then once you have digital superintelligence, there's no point in even reading or learning anything because it'll just be better at everything. And then I think that the robots are going to get very good very quick, and they're going to be using robots to make more robots. And once you have very, very cheap labor in the form of robotics, then everything becomes cheap, right? Building houses is cheaper. Farming is cheaper, cleaning is cheaper, infrastructure is cheaper, like everything becomes cheaper. And like, I think it's all just going to happen very quickly. I think like you don't need to do anything at this point, right? Just enjoy it. Enjoy the transition because soon enough you will just be getting paid money because you're human. We're kind of the last generation of humans, and we're going to be treated like kings by these robots. But at some point, all of the humans will die out, and then there will be the last human who's sitting there in like a VR Neuralink getting fed grapes by a bunch of robots. Or we just eat bugs. Maybe we'll want to eat bugs, right? What if they... biological technology gets better and they create like cockroaches that taste like steak, and then they just farm these cockroaches and then they grind them up into burgers, and you can't tell the difference between a real burger and a cockroach burger. I don't know. What do we think? Huh? 10, 11. I'm already running out of content. I don't know what to talk about. You guys need to give me something weird to talk about, or I'm just going to end the stream here. All right, guys. All right. I'm too tired today. Not enough caffeine, not enough yerba mate. Let's give this a little review. Let's give you guys some time back so you can go work on your projects. Today we did a little short stream called Animals versus Robots. We reviewed this paper here called Animals Can Outrun Robots that really did a nice kind of breakdown of where we're at in terms of biological systems versus electromechanical digital systems. And, it seems like, honestly, we're very close to kind of supremacy. There's still a couple holdouts, but for the large part, in terms of like strength and stiffness and framing, carbon fibers better than bone. In terms of actuation, electric motors are more efficient than muscles, more energy dense than muscles. They can create more power than muscles. In terms of sensing, from a computer vision kind of standpoint, cameras have just as many pixels as your eyes. In terms of speed and latency, so bandwidth and latency, like digital signals can travel faster than biological signals. Biology still has more neurons and more energy efficiency in the neurons. Biology still has more sensors because the sensors are more deeply integrated into the actual muscles and actuation themselves, which allows them to have kind of more decentralized control strategies. And currently right now, the energy density of fat and the conversion of that with mitochondria is more efficient than what we're doing with gas-powered engines and lithium-ion batteries. But it seems like for every single one of these, there is a path forward, and, you know, integrated circuits are getting smaller and smaller and smaller, which means the number of neurons is going to get higher and higher and higher. I think we're going to figure out some kind of swappable situation, or we're going to do some combination of like solar panels, or I don't know. I think this stored energy will get better. There's so much pressure on battery technology now that it's going to get better over time. It's just a matter of time before people figure out like a 2x or even like a 10x improvement in battery technology. That's pretty much it, guys. We looked at some robots. Definitely check out this website. Pretty cool little website that has all the rankings of the robots, especially the creepiest robot ranking. I thought this was kind of clever and fun. But that's pretty much the stream, guys. There's rice steak hybrids. People make steak out of rice. How's it going, Tim? Yeah, I don't know. Cozy stream. Thanks, everybody, for attending. Thanks, Tim, Sarah, Saskia, Godbuddy, Spyro, 87GN, Artem. Scrolling. Tomcat, Ed, Taivu. Thanks, everybody. Short one today, but, you know, I just kind of prepare very little, so sometimes I get hosed like this. Sometimes I pick a paper and it ends up being quite short. But, you know, ain't nobody got time to be preparing too much for these streams, so. Yeah, like and subscribe and join the Discord if you're interested in talking about the future with cool, interesting people. Happy Sunday in North America and Monday in Japan. Peace out, guys.